So we want to prove that n cubed plus 2n is divisible by 3 for all possible values of n that are integer values. So this means for all, do we all remember that? And this means integer values, or in our case positive integer values. What's the first integer?
1.
1? Why not 0?
1. Oh, because it's not a positive integer.
Yeah, it's not positive. It's some would argue it's an integer. I believe the textbook says it is an integer, but it's not positive.
Yep.
0 is neither positive or negative. So if we see z, it can start at 0. If we see z plus, we start at 1. If you decide that 0 is not an integer, that's also okay.
Yeah.
Just fight the examiner if they mark you wrong. Okay, so we want to prove this. What method do we want to use to prove? Proof by
Induction.
mathematical induction. Whenever we're doing mathematical induction, what case do we start with?
The base.
Base case. Base case being the first in our sequence, or that first term in our sequence. So base case. Everything in green. Actually, no, I won't say that. Anyway, in this case, because we're starting at positive integers, it's got to be p of 1. So this is the notation we use for stage 1. For stage 2, I'm going to flip it up a bit, and I'm going to use the subscripted notation, p of 1 like so. You can use what we did in stage 1 if you like, or you can do this. I'm going to do this because I believe that's what the textbook does, and it's what our work solutions are. Alright, so with our base case, all we need to do is we get our statement here, n cubed plus 2n. We're stating that we're working with p of 1. No need to say let n equal 1, it's already inferred here. So it's 1 cubed plus 2 to the power of n, in this, or 2 times n, which is 2 by 1, and it's going to be 1 plus 2 equals 3. So therefore, p of 1 is true. Okay, so we've just shown that if we sub in the first in our sequence, it works, but we haven't proven it yet. Proof by induction requires a base case, and then we need to prove our inductive case. Our inductive case being making the assumption that the case is true, and then showing that the k plus 1th case is also true by extension. If we can prove that our first one is true and our inductive case is true, then we prove that the statement is true using PMI. Alright, now what's our assumption here, Mad Dog?
K is true.
Yeah. Assuming that P of k is true, then what we're going to find is that P of k, what we're going to find is that k to the power of 3 plus 2k is true. Now, if this is true, what's it going to be equal to? 3a. K and A, of course, being positive integer values. Is that cool? Hence, P of k plus 1. And this is where the fun begins. If it's P of k plus 1, then every time we see k, we change it to k plus 1. Remember, we're working with an expression, so this is just our expression here. Next step, what we need to do is we need to somehow configure it in such a way that we show that everything is divisible by 3. To do this, because I can't really work with this guy based on what I have up here, I want to expand this. Now, we don't want to do the slow way because we're stage 2 specialist students. We want to do the fast way. So we're going to use the binomial expansion. Expanding this out, I know that it's going to be k cubed plus 3k plus, 3k squared plus 3k plus 1. That's our cubed bracket. This guy over here is just 2k plus 1. All right, next step.
Isn't it 2k plus 2?
Yeah, of course, I'm just checking that you're watching.
Yeah, of course.
Well done. All right, next step, what we want to do is we want to make it so that we can use our case up here, p of k case. So what I'm going to do is I'm going to get a k cubed and a 2k and throw them out the front. Aside from that is everything else. My 3k squared, my 3k, and my 1 and 2 together. My 1 plus 2. All right, next step. Using p of k. Should always state this because it cues the reader to show that you know what you're doing. Never want the examiner to think you're not as smart as you actually are or knowledgeable as you actually are. So this is going to be k cubed plus 2k is just 3a's. Then we've got all this jazz over here. Our 3k squared plus our 3k plus our 3. Does that seem cool? All right, and it's at this point we run out of board space. So moving across. What coefficient do we have in common across all of our terms over here? Please, Rowan? 3. So because of that, you can see that it's going to be k squared plus k plus 1 plus a. I just moved the a to the back, assuming that's some integer value. Therefore, p of k plus 1 is true. That makes sense? Now, how do we decorate the cake, Lenny?
We did since p of 1 is true and pk is true when pn is true.
Yeah, so it's when p of k plus 1 is true whenever. Then p of n is true. Under what conditions?
O and true positive integer.
Okay, do we have to write everything in English or can we use math symbols as well?
No.
Yeah, we're allowed to use math symbols. If we started at 0, would that be okay? Probably not because it's asking for positive integer values. It wouldn't affect you too badly, but you might lose 1 or 2 marks on the reasoning and communication because it's a misunderstanding of integers. This line over here, setting it to 3a. Could we remember to make sure whenever we do divisibility, we've got to set it to what it's divisible by? Yep. And this stuff over here, any questions? All right, awesome. There's one more complexity to these sort of questions here. We won't go through it just yet, but it will pop up midway through the questions you're working on. When you get stuck, tell me, and I'll show you a cheeky little trick that you may have forgotten from stage 1.